Hi everyone, welcome back to another video of hybridization. This is in continuation of the previous video where we discussed different types of hybridization, definition and examples. In this video we are going to discuss about Vsepr theory, that is valence shell electron pair repulsion theory, and we can also see in the geometry of molecules containing bond pairs and lone pairs. In the previous discussion, we have seen the geometry of molecules, geometry and hybridization of molecules containing only bond pairs. But in this, we are going to see what change in hybridization or what change in geometry can arise when there comes lone pairs. So that shift or distortion in the geometry compared to the expected geometry for molecules containing lone pairs, their examples and the hybridization. And we know whenever there are lone pairs, there will be more repulsion. So the bond angle may change and geometry also may change. So these changes we can detail in the Vsepr theory. So this video is discussing in detail about Vsepr theory, valence shell electron pair repulsion theory and geometry of molecules containing bond pairs as well as lone pairs. Let's see the different postulates of Vsepr theory. The main concepts of Vsepr theory is that the central element in any molecule, central element in the sense, say for example in water molecule we know oxygen atom is the central element, in ammonia nitrogen atom is the central element. So this central element try to arrange its electron pairs, the valence electron pairs around it, around the atom in such a way so that there is minimum repulsion between the electron pairs. And the geometry of a molecule is solely predicted by the arrangement of the electron pairs, the valence electron pairs around the central atom. So we know since they are electron pairs, they offer repulsion among each other, and this order of repulsion is also different for bond pairs and lone pairs. We know for any molecule there can be bond pairs as well as lone pairs. Lone pairs are associated with heteroatoms such as oxygen, halogen, nitrogen, etc. So these bond pairs and lone pairs offer different extent of repulsion, and as per Vsepr theory, the order of repulsion is such that the lone pair repulsion is greatest, and this is greater than the lone pair bond pair repulsion, which in turn greater than bond pair repulsion. So this is the main essence of valence shell electron pair repulsion theory. That means the central atom tends to arrange the valence electrons in such a way that they will have minimum repulsion, and the order of repulsion is lone pair repulsion greater than lone pair bond pair repulsion, which in turn greater than bond pair repulsion. So always remember the lone pairs are offering maximum repulsion to the molecule. So the molecule will adopt a geometry where these electron pairs are kept as far apart as possible to minimize the repulsion and to maximize the energy. So based on these postulates, we can predict the geometry of different molecules, predict hybridization as well as geometry, and the main thing is depending on the extent of this repulsion, it will be having, the compound will be having different bond length. So bond length varies means their geometry of course varies. So these are the main concepts of Vsepr theory. To illustrate this Vsepr theory concept, let's take the example of a simple molecule, say for example Sncl2 Tin Chloride. We know tin atom, it belongs to 14th group, carbon family, and its valence configuration, we know it is carbon, silicon, germanium, tin. So the valence configuration will be, we know for carbon it is 2s2 2p2. So silicon, germanium and tin. So this will be 3s2 3p2, 4s2 4p2 and 5s2 5p2. So the valence configuration of tin atom is 5s2 5p2. So we can see what is the hybridization first. So for tin atom, central element tin, the ground state configuration is 5s2 5p2. And we know in order to combine with two chlorine atoms, the tin atom should make available two half-filled atomic orbital, but here already there are two half-filled orbitals, so there is no need of any excitation. As such, it can undergo or it can make available the half-filled atomic orbital. So the hybridization involved in this will be sp2 hybridization. Always hybridization, we can have hybridization like sp, sp2, sp3, sp3d and so on. So in this case the hybridization will be sp2. And sp2 hybridization, we know the standard, if you have only bond pairs, and sp2 hybrid, a typical sp2 hybridization will be having a central element, let's say X, having a trigonal planar arrangement of hybrid orbitals. So this is the case for a typical sp2 hybridization. We have three hybrid orbitals with trigonal planar geometry, but in this case there are three hybrid orbitals, but one of the hybrid orbitals contain lone pair. So this is the case in the case of tin central element. We have three hybrid orbitals and one of the hybrid orbital contain lone pairs, and the other two hybrid orbitals are having one electron each, and which is available for bonding or overlap with two chlorine atoms. So here what happens, we know this is the tin atom. So for tin atom, we have two half-filled hybrid orbitals and we have two chlorine atoms. Two chlorine atoms needs to combine with the half-filled hybrid orbitals of tin. So each chlorine atom with 3pZ1 configuration will now overlap with the hybrid orbitals of tin to form a bend geometry. We can see here, since there is a lone pair, it will be having a bend shape. Okay. So for sp2 hybridization, if we have only bond pairs, the expected geometry would be trigonal planar, but in this case the sp2 hybrid orbitals, one of the sp2 hybrid orbitals are having the lone pair of electron. So the lone pair will not be contributing towards predicting the geometry. In order to predict the geometry of any compound, we should consider only the bond pairs. So here we have two bond pairs and one lone pair. So the shape of the molecule or the geometry of the molecule will be bend shape or V shape. So this is the geometry. Here the bond angle would be slightly less than 120 degree. We know the typical trigonal planar structure would have a 120 degree bond angle, but in this case there is a lone pair also. We know as per Vsepr theory, the lone pairs offer higher repulsion. So in order to minimize the lone pair bond pair repulsion, these two bond pairs are shrink towards each other a little bit, and their bond angle would be less than the expected bond angle, that is 120 degrees. So here the bond angle of Sncl2 is slightly less than 120. So this is the geometry and hybridization for Sncl2. So when we compare, initially when we have Sncl2 molecule, it seems to be a linear geometry, because we have beryllium chloride molecule, it is having linear geometry. But in the case of Sncl2, we must remember that the tin molecule tin atom is having a lone pair. So it is an example for a molecule having two bond pairs and one lone pair. So because of the presence of lone pair, its geometry would be bend shape with a bond angle slightly less than 120 degree. Next, let's take the example of ammonia molecule. In the case of ammonia molecule, we know nitrogen atom is the central element and the ground state configuration of nitrogen atom is 2s2, 2p3. So we have 2s2 and 2p3. In order to combine with 3 hydrogen atom, the nitrogen should make available 3 half-filled orbitals, and we know already there are 3 atomic orbitals, so these will hybridize. It will be the hybridization is in such a way that one of the s orbital, we know valence shell contain 2s2 and 2p3. So the s subshell and the p s orbital and the 3p orbital undergo hybridization to give sp3 hybrid orbital. We know sp3 means we have 4 sp3 hybrid orbitals. Out of the 4 hybrid orbitals, one of the orbitals contain lone pairs and others are half filled. So since we have nitrogen atom with sp3 hybrid orbitals, they will be arranging in a tetrahedral manner. Okay, we will have a tetrahedral arrangement of sp3 hybrid orbitals, but in this case one of the orbital contain lone pair. So because of the presence of lone pair, the geometry of the molecule will move or will shift from the expected tetrahedral shape to a pyramidal shape. So here one of the since one of the hybrid orbital contain lone pair, that will tend to offer high repulsion, and in order to reduce the repulsion, the 3 hybrid orbitals containing half-filled or 3 hybrid orbitals containing 1 electron each will tend to arrange themselves in a pyramidal manner. And now to the 3 orbitals there will be overlapping of each hydrogen atom with 1s1 configuration with the half-filled hybrid orbitals of nitrogen atom to form a pyramidal ammonia molecule. So this is the geometry of ammonia molecule. We know the lone pair is not contributing towards the geometry of the molecule. Geometry is solely determined by the bond pairs. So this is the case of ammonia. We have nitrogen atom with configuration 2s2 2p3 and the hybridization will be sp3. We have 4 hybrid orbitals, but one of the hybrid orbitals contain lone pairs. Because of the presence of lone pair, the other 3 orbitals will tend to arrange in a trigonal pyramidal manner, and we will get a pyramidal structure of ammonia molecule with a lone pair, and each hydrogen atom with 1s1 configuration overlap with the half-filled hybrid orbitals to form the ammonia molecule. So this is the case with ammonia. In the same way, we can explain the formation of water molecule. And remember that for ammonia molecule, the bond angle is 107. It is nearly 107 degree. And now let's take water molecule. For water molecule, we know central element is oxygen, and oxygen is having a ground state configuration, valence configuration 2s2 2p4. So the valence configuration is 2s2 2p4, and we know in order to combine with 2 hydrogen atom, this oxygen should make available 2 half-filled orbitals, and there are already 2 half-filled orbitals, so it undergo the same sp3 hybridization, but here we have 2 lone pairs. In the case of ammonia molecule, then also it was sp3 hybridization, but there was only 1 lone pair, but in this case there is sp3 hybridization and 2 lone pairs. So we have central oxygen and there will be 2 lone pairs and 2 of the hybrid orbitals contain 1 electron each. Now, with this half-filled hybrid orbitals, the two hydrogen atom with 1s1 configuration overlap, resulting in a bend-shaped water molecule. Bend-shaped water molecule with central atom having two lone pairs. So we have in water molecule there are two bond pairs and two lone pairs. Because of the presence of two lone pairs, these two bond angles will still shrink towards each other, and the bond angle will be nearly 104 degree. In the case of ammonia, we had only one lone pair, so the bond angle was little more widened to 107 degree, but here in water molecules, because of the presence of two lone pair, we have high extent of lone pair repulsion, and also there is lone pair bond pair repulsion. So because of this, these two bond pairs shrink towards each other to make the bond angle 104 degree, so as to have minimum repulsion between the bond pairs as well as the lone pairs. So this is the structure of or geometry of water molecule: bend shape or V shape, and sp3 hybridization, bond angle 104 degree. And for ammonia molecule also, hybridization is sp3, geometry is pyramidal shape, and bond angle is 107 degree. Next, let's take the example of xenon dichloride. Xenon, we know it's an example for a noble gas. The noble gases are helium, neon, argon, krypton, xenon and radon. So for xenon, the ground state configuration is 5s2, 5p6. Being a noble gas, it is having completely filled configuration. But we know among the noble gases, only xenon form compounds. So its configuration is 5s2, 5p6 and 5d0. And since all the electrons are paired, there are no electrons or there are no orbitals available for orbital overlapping. In order to overlap or in order to bond with another atom, we should have half-filled atomic orbital. So here, in order to combine with two fluorine atom, the xenon atom should make available two half-filled atomic orbital. So for that, one of the electron from p orbital undergo excitation to the d subshell. So the excited state configuration, this is the ground state configuration, and the excited state configuration will be 5s2, 5p5 and 5d1, and the hybridization, resulting hybridization will be sp3d. We have sp3d hybridization. We know for molecules containing bond pairs alone, for sp3 hybridization, we have 5 hybrid orbitals, and the favored geometry for 5 hybrid orbitals is a trigonal bipyramidal geometry. So here also, this will adopt the 5 hybrid orbitals will arrange in a trigonal bipyramidal manner with 3 of the orbitals contain lone pairs, and only two are having half-filled electrons. So this is the case for xenon atom in the ground state. We have two atomic orbitals, two hybrid orbitals are half-filled, and they are occupying the axial position, while the equatorial orbitals present in the equatorial position are having the lone pairs. So this is the way in which it can have least repulsion or maximum stability, by arranging the lone pairs, 3 lone pairs in the equatorial plane, and the 2 unpaired electrons, 2 half-filled orbitals in the axial plane. So now we know each fluorine atom, we have 2 fluorine atoms, so each fluorine atom with 2p-side configuration will now overlap with the xenon atom, with the half-filled hybrid orbitals of xenon atom, to form a xenon difluoride molecule. So there will be overlapping of two of the fluorine atoms with configuration 2pz to form xenon difluoride molecule having linear geometry. So here the geometry is linear and the hybridization is sp3d. For sp3d hybridization, we know there are 5 hybrid orbitals, and among the 5 we have 3 equatorial hybrid orbitals and 2 axial hybrid orbitals. And here, in order to reduce the repulsion, the 3 lone pairs are occupying the equatorial position and the 2 bond pairs are in the axial position, resulting in a linear geometry for xenon difluoride molecule. Next, let's take the example of xenon tetrafluoride, XeF4. In the same way we have done xenon difluoride, we can do here also for xenon tetrafluoride. For that, we should write the valence configuration 5s2, 5p6, 5d0. Ground state configuration is this one, 5s2, 5p6 and 5d0. In order to combine with 4 fluorine atom, xenon should make available 4 half-filled orbital. So 2 of the electrons from the p subshell will be promoted to the d subshell in the excited state. So the configuration will be, excited state configuration become 5s2, 5p4, 5d2, and here the hybridization will be sp3d2. We know generally for sp3d2 hybridization with 6 hybrid orbitals, the favored geometry will be octahedral. We will have 6 orbitals, 3 plus 2 plus 1, total 6 orbitals, 6 hybrid orbitals. So they will have lowest energy when they arrange themselves in an octahedral manner. But in this case, we know there are 2 lone pairs. So the 2 lone pairs are also present, and because of the presence of 2 lone pairs, the molecule will be having a square planar geometry. So the 2 lone pairs are occupying above and below the plane of the square, and the 4 orbitals are in the plane of a square, or they are having a square arrangement. And now we know each of the fluorine atom with 2pz configuration will overlap with the half-filled hybrid orbitals of the xenon atom to form the xenon tetrafluoride molecule having square planar geometry. So when you have 4 bond pairs and 2 lone pairs, the molecule will adopt a square planar geometry. So this is the case with XeF4. We have xenon atom, the ground state configuration is completely filled. In order to bond with 4 fluorine atom, it will make available 4 half-filled atomic orbitals, and these all will hybridize to form 6 sp3d2 hybrid orbitals, and among the 6, 2 are occupied by lone pairs. So because of the presence of 2 lone pairs, it will deviate the xenon tetrafluoride or xenon atom with 6 hybrid orbitals would deviate from the expected geometry octahedral to square planar geometry. So we will be having 4 bond pairs and 2 lone pairs with square planar geometry. One more example we can see, that is IF5. In the previous video we have seen IF7, that was an example for a molecule having only bond pairs, but in this case there is a lone pair also. So let's see what change in geometry is expected when there is a lone pair also. So the ground state configuration of iodine is 5s2, 5p5 and 5d0. And we know In order to combine with 5 fluorine atom, this iodine atom should make available 5 half-filled orbital, but only one is present. So what happens is 2 of the electrons will be promoted. 2 of the electrons from 5p will be promoted to 5d level, and the excited state configuration become 5s2, 5p3 and 5d2. So now these undergo hybridization to form sp3d2. So we will get sp3d2 hybridization, and we know in the previous case also we have seen sp3d2 hybridization, but that contain the xenon tetrafluoride that has 4 bond pairs and 2 lone pairs. Whereas in this case we have 1 lone pair. Okay, one of the hybrid orbital contain lone pair and the others are becoming bond pairs. So the geometry of the molecule will be, let's see, here one of the orbital contain lone pair, all other contain half-filled orbitals, and each fluorine atom with 2pz configuration will now overlap with the half-filled hybrid orbitals of the iodine to form IF5 molecule with a square pyramidal geometry. So here the geometry will be a square pyramidal. We have IF5 molecule with square pyramidal geometry, that is we have 5 bond pairs and 1 lone pair. So whenever you have 5 bond pair and 1 lone pair, it will have square pyramidal geometry, and in the case of HCF4, 4 bond pairs and 2 lone pairs, it is square planar. Now let's conclude all these. We can see the different types of molecules having different number of bond pairs and lone pairs and their corresponding geometry. So this represents the type, that means AB2, AB2L. Here the B represents bond pairs and L represents lone pairs and their corresponding geometry. For AB2 type, that means only 2 bond pairs, no lone pair, so the geometry will be linear. Example, we have seen beryllium chloride molecule. And for AB2L, that means 2 bond pairs and 1 lone pair. Example, we have seen a Sncl2, the geometry will be bend shape. And for AB2L2, that is 2 bond pairs and 2 lone pairs, as in the case of water molecule, the geometry will be bent, again bend shape. But the bond angle will be different in both these cases. And we have AB3, that is 3 bond pairs and no lone pair. Example, BF3 molecule. And the geometry would be trigonal planar. And for AB3L type, that is 3 bond pair and 1 lone pair, we have example ammonia molecule, and the geometry is pyramidal. And another type is AB3L2. This AB3L2 actually we didn't discuss in the hybridization part. This is 3 bond pairs and 2 lone pairs. We can derive in the same way we have done for sp3d hybridization. Here also it is sp3d hybridization. We will have 5 hybrid orbitals, but 2 are having lone pair and 3 are having bond pairs. So it will be having a T shape. T shape means we will have a trigonal bipyramidal arrangement where 2 of the equatorial bonds, 2 of the equatorial hybrid orbitals and the 2 axial orbitals, the shape will be like Cl F3. ClF3 is a typical example. So we have 2 equatorial bonds, 2 equatorial hybrid orbitals contain the 2 lone pair, and the third equatorial hybrid orbital will be bond pair. So this way it will get the T shape. So that is the geometry of molecule containing 3 bond pairs and 2 lone pair. Shape is T shape, example ClF3. And finally, then we have Ab2L3 type. Ab2L3 means we have 2 bond pairs and 3 lone pairs. Example, we have seen XCF2, Xenon Dichloride. Its geometry will be linear. Next we have AB4 type. AB4 type means we have 4 bond pair and no lone pair. Geometry will be tetrahedral. Example, we have seen methane. Then AB4L2, that means 4 bond pairs and 2 lone pairs. The geometry is square planar with example XCF4. Xenon tetrafluoride, we know it is having square planar geometry. Then we have another type AB4L. This also we didn't discuss in the description. AB4L means we have 4 bond pair and 1 lone pair. It is also having sp3d hybridization, but the shape geometry will be seesaw shape. Example, let's say SF4. SF4 molecule, we have so this will be the arrangement. That means we'll have 5 hybrid orbitals, sp3d, so 5 hybrid orbital. One of the equatorial hybrid orbital contain lone pair, all the others are bond pair. So the actual geometry would be seesaw shape. So that is the case of 4 bond pair, AB4L type, that is 4 bond pair, 1 lone pair, seesaw shape, example SF4. Then we have AB5 type, that is 5 bond pair and no lone pair, trigonal bipyramidal. Example PCl5, phosphorus pentachloride. Then we have 5 bond pair and 1 lone pair, AB5L type. Example square pyramidal. We have seen IF5 example, IF5. And AB6, that is 6 bond pair and no lone pair. Example the geometry is octahedral. So octahedral geometry, we have seen SF6 sulfur hexafluoride. And finally AB7. AB7 means 7 bond pairs and no lone pair. So the geometry will be pentagonal bipyramidal. Example IF7. So these are the different types of different molecule types and their corresponding geometry. So we can see in all these cases that based on the number of lone pairs or with changes in the lone pair, number of lone pair, there can be deviation from the expected geometry in order to minimize repulsion and getting maximum stability. Now let's summarize all these portions that we discussed today. So today we have discussed the Vsepr theory, that is valence shell electron pair repulsion theory, its different postulates, and the geometry of molecules containing lone pairs and bond pairs, their hybridization and different types of molecules. That means different bond types, say whether it is AB2L, AB3L2, AB5. So whatever be the type, we can predict their geometry based on the number of bond pairs and lone pairs. So we can also calculate or we can also derive their hybridization, and from the hybridization, by knowing the number of lone pairs, we can predict their actual geometry also. So these are the essence of Vsepr theory and geometry of molecules. Hope you all understood all these. If you have any doubts, you can put your questions and comments in the comment box. Thank you all for watching.